In this lesson, we're going to cover what's called the fundamental theorem of algebra. The fundamental theorem of algebra tells us how many numbers of solutions there are in any polynomial equation. And then we're going to use this with the conjugate theorem to help us write equations for polynomials. We'll hold off on graphing. We'll do this in a next lesson. So let's start off with the fundamental theorem of algebra. The concept is super easy. A polynomial of degree n has exactly n solutions for the equation when we set f of x is equal to 0, our polynomial is equal to 0. There are n different values of x which make this true, and this is when we count repeated solutions. So I'll talk about repeated solutions in just a bit, but when we say that there are n solutions, it's including the repeated solutions. Now when we talk about solutions, other synonyms we've been talking about, solutions for f of x is equal to 0. We also call them zeros. There are n zeros. There are n factors for any polynomial of degree n. So let's look at an example here. Here is a polynomial. It's written in a different kind of form, but it is a polynomial. And if you can see this we're going to have an x to the third here times the x. So this is going to be a fourth order polynomial. And if we were to expand it out, we can actually see from this expansion of factors, we actually have 1, 2, 3, 4 different solutions for this. 3 of them are repeated factors. So this is what I mean by repeated solutions, repeated factors. So we do have 4 solutions for our fourth degree polynomial. 3 of them are repeated though. We have 4 factors. Again, it means we have 4 solutions to this equation. If I want to set this equation to 0, there are 4 solutions. Here we have an equation, a 7th degree polynomial is equal to 0. How many solutions are there? According to the fundamental theorem of algebra, we have 7 different solutions, again, counting the repeated ones as well. So it's a very simple concept. All you need to do is look for the highest order. That's how many solutions you have. Again, let's look at this one. Let's scan across. We have x to the 6th being our highest exponent. So there are 6 different solutions, 6 different zeros. This is just a different word. They mean exactly the same thing. 6 different solutions for this function. You notice here the difference between the two lines. In this case here, I have an equation equal to 0. There are 7 solutions for this. In this case, I have a function, and this function has 6 zeros, meaning when I set it equal to 0, when this function is equal to 0, let me just even write that down, when f of x is equal to 0, there are 6 different solutions to that. Okay, so these are some very simple problems for you to do on your own. Let's move on to what we call the conjugate theorem. The conjugate theorem states this. If I know that a plus bi is one of the zeros, one of the solutions to f of x is equal to 0, then I also know that a minus bi is also a 0. We also can say the same thing, assuming, this is a kind of a key case, assuming we have rational coefficients for our polynomials. If a plus square root of b is one of the zeros, then we also know that its conjugate, a minus square root of b, is also 0. And just as a kind of example, we see the quadratic equation, quadratic formula, b plus or minus the square root of b squared minus 4ac over 2a. This kind of implies right here, or we could see the conjugate theorem being kind of at play here with the quadratic formula itself. So when you have a polynomial, x squared, we actually have 2 solutions sometimes, depending on the discriminant. When it's less than 0, we have 2 complex conjugates. When this is a positive number, and when this is a positive number, which doesn't have a perfect square root, we end up having 2 rational or 2 radical conjugates instead. So here's an example of how we can apply this. Suppose we want to write a polynomial function with the following zeros and a leading coefficient of 2. We're given that one of the zeros is 2, another one of the zeros is 3 minus 2i. This means that there is an additional 0, that being the conjugate version. 3 plus 2i is also going to be one of the zeros. So now let's take this knowledge of all the zeros and write an equation. And we're going to use kind of an intercept form-like form. We've seen when we have a quadratic, when we have x minus p, x minus q, we called that intercept form. Now we're going to look at the case where we have more than one zero, or more than 2 zeros. We have 3 in this case, so I could write this 0 as a factor x minus 2. I can write this factor, or this 0 as a factor x minus 3 minus 2i, and this other one I could write as x minus 3 plus 2i. So I have 3 factors here, and this is something we haven't seen in the past, a factor which has a complex number in here. But we can write this out like this, and now we're going to expand it out. This is where we do some arithmetic stuff. We're going to rearrange this term here. I'm just going to move the parentheses around. I have x minus 3 here, and I changed the sign here from a minus to a plus, because this minus sign really gets distributed. This is x minus 3 plus 2i, and so I rewrote it like this, and I rewrote this other one like this, and you'll see why in a second. Actually, hopefully this construct looks, you can see within this structure a plus b, a minus b type of structure that we can then rewrite as the difference of perfect squares. So the next line, we have now expressed this as a squared minus b squared, and I can now re-express 2i squared as negative 4, so minus negative 4 becomes plus 4. And now I'm going to multiply out this these 2 multiplications of polynomials, and I'm going to expand this. So I got x times this whole polynomial is this polynomial in purple. Negative 2 times this polynomial here is this red part of the polynomial. And now I'm going to add the like terms together, and now I have my standard form polynomial function that has the zeros 2, 3 minus 2i, 3 plus 2i, as well as this leading coefficient of 2 right at the beginning here. Okay, so that's the lesson for today. I have this one other problem that you can go ahead and work out now or in class. Okay, thanks.